You have learned that a system is a part of the universe in which observations are made. In order to make these observations, it is important that we know the state of the system. By state of a system, we mean the condition of the system in terms of measurable, macroscopic properties such as temperature T, pressure P, and volume V, to name a few. The first state of the system, that is, the state before the change, is called the initial state, and the last state, that is the state after the change, is called the final state. As a change in the magnitude of these properties changes the state of a system, these properties are called state variables or state functions. In other words, properties whose values depend only upon the initial and final states of the system and are independent of the manner in which the change is brought about are called state functions. Macroscopic properties, on which the state of a system depends, are further divided into extensive properties and intensive properties. Extensive properties are properties that depend upon the quantity of the matter contained in a system. Examples of extensive properties are mass, volume, and heat capacity. For example, 200 milliliters of water takes up more volume than 100 milliliters of water. Intensive properties are properties that are independent of the amount of the substance present in the system. Some examples of intensive properties are temperature, pressure, freezing point, and boiling point. For example, boiling point is an intensive property because whatever be the quantity of water, it always boils at 100 degrees Celsius. When the state of a system changes, it implies that some thermodynamic process has occurred on the system, and energy has been either added to it or removed from it. The energy stored within a substance or a system is known as the internal energy of the system. In other words, internal energy is the sum of all the possible kinds of energy of a system. Internal energy is represented by capital U. The absolute value of internal energy cannot be found. However, change in it, represented by delta U, can be found. Internal energy U changes when work is done on or by the system. Heat passes into or out of the system. Matter enters or leaves the system. Let us discuss the change in internal energy brought out by work done on the system. Let us take a certain amount of water in a thermos flask or an insulated vessel that does not allow heat exchange with the surroundings. Such a system is called an adiabatic. The state of such a system changes without an exchange of heat, and thus the process is called an adiabatic process. In other words, delta Q is equal to 0. We can bring a change in internal energy in a system by two ways. In the first method, internal energy can be increased by doing some mechanical work. For example, by churning the water. Let UA be the initial internal energy of the system at temperature TA. After churning, internal energy changes to UB as temperature increases to TB. Thus, The change in internal energy is given by delta U is equal to UB minus UA. In the second method, internal energy can be increased by the same amount by doing electrical work. In this, an immersion rod is kept in water and the temperature before and after is measured. We find the change in temperature as TB minus TA. Hence, the change in internal energy, delta U, equal to UB minus UA. Thus, internal energy changes to the same extent either by doing mechanical work or electrical work, which indicates that it is independent of the manner in which the change is brought about. Therefore, internal energy is a state function. If work is done on the system, then U increases and W is considered as positive. On the other hand, if work is done by the system, then U decreases and W is considered as negative. A change in internal energy can also be brought out by the transfer of heat. Heat transfer takes place from the system to the surroundings, or vice versa. The exchange of energy due to temperature difference is called heat Q. Therefore, delta U is equal to Q. Q is positive if heat transfers from the surroundings to the system, and negative if heat transfers from the system to the surroundings. If heat transfers from the surroundings to the system, then internal energy increases, and hence Q is considered as positive. On the other hand, if heat transfer takes from the system to the surroundings, then internal energy decreases. That is, Q is negative.